Hi, I'm Bill Kinney, and in this video I'm going to get into the details of how to make a Mathematica demonstration of something that was on my favorite YouTube channel, 3Blue1Brown by Grant Sanderson. Back in August of 2018, Grant uploaded a video where he demonstrated the equivalence of the conic section definition of an ellipse with the constant sum of focal distances definition based on something called a Dandelin sphere. Now, if you're not familiar with these things, probably the best place to start is Grant's video. As usual, he just does a great job of explaining things visually. You really see the geometry behind why these two definitions are equivalent, and it really motivates you to want to study more. Okay, my purpose is different. I want to take an analytic geometry approach to this, which means coordinates, variables, equations, especially the quadratic formula will be necessary. So it does make it more difficult. I'm also using this program Mathematica that you see, so I want to talk about how to program it. As far as math prerequisites, technically speaking, I don't do any calculus in this video. However, knowing calculus, knowing about graphs of functions, including graphs of functions of more than one variable in multivariable calculus is definitely helpful. And definitely having some Mathematica experience is helpful. If you don't have those things, it's going to be tough sledding, but you can do your best anyway if this really interests you. Before we get into the content of my video, and I think I'll put a timestamp for the content down below for when that starts, I have some introductory stuff that I want to say here. First of all, what is Grant's video? It's this one. It's called Ever Wondered Why Slicing a Cone Gives an Ellipse? It's wonderfully clever. That's his video from August of 2018. I also want to alert you to my channel, Bill Kinney in Math. I've got hundreds of videos about math. They fall into three categories. I've got 50 to 60 minute lecture videos, my most popular being real analysis and a few on financial math, and then I've got also lectures on complex analysis, statistics, abstract algebra. I'm going to probably in the future do more on probability. I also have videos, problem-solving videos, including problem-solving videos from multivariable calculus, real analysis, lots of them on financial math that I've been doing recently. And then I've got videos where I focus on Mathematica usage, how to program Mathematica. Mathematica is real important to me. It helps me understand things. It helps me solve problems that I couldn't do so otherwise, and this problem that we're looking at here is an example of that. Finally, another introductory comment is just here in 2019 I've started a blog called Infinity is Really Big. So far my content mostly involves financial math and real analysis. You can look through these here. I'd encourage you to check that out. The article I'm working on right now is about this video that I'm making right now. Why does slicing a cone give an ellipse? So it's a more general interest article. Get into some of the algebra details. Here's the key picture. I've got Grant's video embedded, and this video I'm making right now is going to be inserted right here after I finish it. So yeah, please, I would encourage you to check that out. Lots of equations here to help you understand what's going on. Lots of use of the quadratic formula. To help us get going on understanding the Mathematica, we're going to also be using this picture that you see here. It's a two-dimensional version of the three-dimensional problem. That's a general problem-solving strategy, especially when things are in higher dimensions. To understand what's going on in higher dimensions, use a lower dimensional version of that. Alright, let's do the Mathematica now. I probably should start off with the demonstration right away here just to show you what the end product is. Where are we headed? That's in this section here. You might wonder if you're familiar with the Wolfram Demonstrations project. Am I going to post this on there? The answer is I'm not sure. I might not. Let's go ahead and enter this code, and then let's talk about this picture that you see here. This is the key picture. What do we see? First of all, you see this blue cone, and then you see this plane slicing the cone. The intersection forms what's called a conic section because you're slicing a cone. And that intersection is what you see here, this oval shape that's partially colored orange when y is positive and brown when y is negative. Y goes into the screen here, positive going into the screen. That is the ellipse, that is the intersection. You also see a couple pinkish magenta dots here. Those are the foci of the ellipse. foci being plural of focus. Then you see some lines in here, and you see some sliders up here. The Mathematica demonstration has interactivity. You can move these sliders. I can change X, for example, and that changes where the black dot is on the ellipses, changes these lines. And the focal definition of the ellipse, think about it here. If you look at the black dot and compare it with the two foci, and look at the line between the foci and the black dot, the sum of those two distances has to stay constant no matter where the black dot is on the ellipse. That's the sum of the focal distances definition. And Grant's key insight in his video is that these two yellow lines have the same length and these two red lines have the same length, and the yellow plus the red along the side of the cone here definitely has constant length because the distance between these circles stays constant. And that's the key insight of his video, based on these green spheres, which are called Dandelin spheres, whose points of tangency to the plane are these pinkish magenta dots. Technically the color is magenta there. I can also, in my interactive demonstration here, change the slope of the plane like that to get a different ellipse of intersection. I can also change the vertical intercept to be different things as well, and no matter what they are, you still get an ellipse, okay, with different eccentricities. All right, now let's get into the details of how to program that. And again, these details are pretty complicated. You're going to want to get ready and really get excited about doing this if you're going to make it through to the end here. And again, you really should have some Mathematica experience. I will talk about some Mathematica issues, but it's probably too much to fully understand if you've never done Mathematica before. First, what I'm going to do is I'm going to think about the two-dimensional picture here. I'd like to start by making a graph, a function whose graph is this blue upside down V. In fact, I'm calling it UDV for upside down V. It's a function of x. Notice when you define a function in Mathematica, you need to put an underscore after the variable. That is essential. You also use square brackets in Mathematica for function arguments, not parentheses. And it's good practice, typically, instead of doing an equal sign here, to do a colon equals. How do you make an upside down V? Well, a right side up V is the absolute value function, so if you put a negative sign in front of it, that's going to be a function whose graph is an upside down V. Left and right correspond to just the lines on the left and right side of the upside down V. I've got another reason for that. But as far as plotting this function goes, now I just plug it into the plot command. In the way you see here, x is going to go between -5 and 5. All this stuff is just formatting stuff. I also have some other formatting commands going on behind the scenes here that you're not seeing that make the axes, for example, extra dark. Don't worry about that. That is our starting point. There is our upside down V. This is the two-dimensional version of the three-dimensional cone. If you imagine rotating this around the z-axis in a third dimension, you will get a cone. Okay, this is partially a warm-up, but it's partially problem-solving for getting us toward what we want, this Mathematica representation of what goes on to get that demonstration that I showed you. What we see here next, excuse me, is a function whose graph is a line. The red line over in this graph, z equals mx plus b. I'm using z instead of y for a reason. Y is going to kind of be going in and out of the screen for the three-dimensional picture. I do want to keep in mind that I'm going to go ahead and take the slope to be between 0 and 1. I mean, I could take a negative slope if I wanted to, but you know, it's good enough to consider this picture with a positive slope. The slope being bigger than 1 really doesn't give you the kind of picture that you want. We have also a vertical z-intercept at b, where b actually is negative, and that's going to be worth remembering. You might want to write that down if you're taking notes. B here is going to be negative. I mean, I could have written this as z equals mx minus b, where b is positive, but I took it in the standard form. I just want to keep in mind b is negative here. This intersection of the red line with the z-axis is below 0. Okay, that'll be important to remember. Notice in this function here, x is the main variable. I put m and b as subscripts here. I didn't actually have to do that, but conceptually, in my mind, it's a good idea because it reminds me that those are kind of parameters that can change, and different values of m and b give me different lines. Okay? But if I plug in specific values for m and b, like m is 0.5 and b is negative 1.5, then I can put it in the plot and get a plot of a specific line. But now to make an interactive, dynamic graph, I need to put that plot inside a manipulate. Manipulate is the key Mathematica command to make dynamic content. Notice I have the entire plot here with an arbitrary m and b, effectively inside the manipulate, with this code here meaning m and b are going to be they're going to be sliders that can vary. M is going to start out at a value of 0.5 and can vary as low as 0.1 and as high as 0.9. B starts at a value of negative 1.5 and can vary as low as negative 3 and as high as negative 0.5. So this again will make dynamic content that you can move the sliders to change what happens. Okay, and you can slide them, you can also play them like that to get a movie. Though we'll see, I won't show it to you, but the three-dimensional picture, it kind of bogs down a little bit. It's not so good to play it as a movie because there's so much computation going on. All right, with me so far? Now we get a little bit harder. The graph of a circle, one of these green circles, has a special equation. Since it's centered on the z-axis, its equation could be thought of as x squared plus, in parentheses, z plus k squared equals r squared. If k is positive, that will actually have an center at 0, negative k, like I say here. Setting that equal to r squared is an equation of such a circle. However, what I'd like to do is I'd like to think of that as a function of two variables whose level curve at output 0 is the circle. In other words, this function, circle of two variables x and z, is a function such that if I set it equal to 0, the curve of points where that occurs is the circle, the curve in the xz plane. Again, that's basically equivalent to the equation x squared plus z plus k squared equals r squared. Where does this function equal 0? And in contour plot is something that will then plot that. Contour plot, where does this function equal 0? In the case where k is 3 and r is 2 here, k again is the means the center of the circle is at 0, negative k, in this case 0, negative 3, and r2, which is 2 here, is the radius of the circle. And I can put this in a manipulate as well. Manipulate this contour plot right here. K starts out at 3, can go between 0.5 and 5. R starts out at 2 and can go between 0.5 and 4, and that makes an animation. So that's one way you can make the circle and animate it. It's going to turn out, this is a bit confusing, for the three-dimensional picture, because the animations can get bogged down, that you want something that can render faster. And when you do contour plot 3D, there's so much computation going on with it that it renders kind of slowly. So there's an alternative way to do it that'll be better for 3 dimensions here. Now this is complicated to explain it. I don't really want to explain it. Graphics is just another way of making graphs, in this case a circle, that won't be so computationally intensive. Again, it doesn't make a big deal for the 2-dimensional picture, but this is going to be a bigger deal for 3 dimensions. Okay, so I'll just mention that. It's not really something to worry about too much. All right, what am I after next? So I've got functions whose graphs will be the blue lines, the red line, and the green circles. I'd like to get these points in here, these colored dots. The black dots, the orange dots, the pink dots. The black dots are the intersection of the red line with the blue lines. The pink dots are the points of tangency, which are the same as the points of intersection between the green circles and the red line. And the orange dots are the points of tangency, which are the points of intersection of the green circles with the blue lines. Let's focus on the intersection of the green circle with the blue lines first. And it's going to be helpful to use, come up with functions whose graphs are, say, the upper halves of these circles. Now you can solve the circle equation for z as a function of x and get these two answers. The one involving the plus sign is the upper semicircle, the one involving the minus sign is the lower semicircle. So I can create new functions of x with k and r as being parameters using those formulas. And it's upper circle, and I could make plots that combine those two things to make a plot of the circle. I purposely made them different colors here to see that the upper semicircle is magenta or pink and the lower semicircle is brown. And I can make and manipulate as well. I think I won't bother entering that. But what I'm after now is where are those points of tangency? So what am I doing here? I'm using Mathematica's solve command, which does algebra. Set the upper semicircle of an arbitrary semicircle centered at 0, -k and of radius r equal to the left-hand blue line, which has equation z equals x. Get two answers. And also solve where an upper semicircle for an arbitrary such circle equals the right side of the blue graph, which is the line z equals -x, and get two slightly different answers. Okay? Now here's where we start to get a little bit more challenging as far as understanding what's going on here. An arbitrary green circle centered on this z-axis with an arbitrary radius, say large radius, is going to intersect typically, well, at least if you extend these blue lines further, these blue lines at more than 1 point, 2 points, each blue line if you extended it further. Okay? But in order to be tangent to those blue lines, these circles have to just intersect each one at 1 point. We got 2 points here for each one, this one and this one. Where will those only give 1 point? You only get 1 point when the thing under the square root is equal to 0. Okay? So that's the condition. When that's 0, that will guarantee that these circles are tangent to the blue lines, and in 3 dimensions, the spheres are tangent to the cone. When that's 0, -k squared plus 2r squared equals 0, which, since k and r are positive, is equivalent to k equals square root of 2r. And that results in points of tangency whose coordinates only depend on r, which is good. It'd be nice to be able to get rid of the k's, so to speak. Okay? For these circles, and ultimately in 3 dimensions, the sphere, k really depends on r, so we can get rid of the k. That's one good thing. The other thing we're after is ultimately getting everything in terms of m and b, the slope and intercept of the red line, and ultimately the red or pink plane in 3 dimensions. That's where we're headed. Keep that in mind. What am I going to do here? To be able to plot those points, which are the ones in orange here, I want to use these formulas that I have here, plugged in this way. Notice the curvy braces. Okay, in Mathematica, that's called a list. Lists can be used and interpreted lots of different ways. One way they can be used and interpreted is as points. I'm not using parentheses. Okay. By the way, once you've got one of these functions inputted like this, you can use it. You can plug in a specific value of r, for example, and get an output. So that would represent the point whose coordinates are -3/√2, -3/√2. Okay? Just to understand what's going on here. That's going to help me plot those points. The orange points for both circles. What about the magenta points, the pink points, points of tangency of the circles with the red lines? This gets a bit more complicated, especially if you were trying to do it by hand. So here, besides the graphs and the dynamic interactivity, we really are seeing more of the usefulness of Mathematica. I need to solve for where an upper semicircle of an arbitrary radius equals an arbitrary line of slope m and vertical intercept b. Doing this by hand, it's not impossible. You could do it. It does involve the quadratic formula, but you can see the answers here are pretty complicated. Be very likely to make a mistake. Okay, Mathematica is definitely handy for that. So we have, for any individual green circle of this form, evidently 2 points whose x-coordinates are given by these things, where the green circle would intersect the red line, at least if the circle is big enough and in the right spot. But once again, we want a point of tangency. We only want one solution for each of these circles, one pink point for each circle. So once again, we're going to need to think about when is the thing under the square root 0, so that the plus or minus here and here don't matter, so to speak. We only get one answer. Before I go on, I should also say the k over 2 here came from setting the thing under the square root equal to 0 back up here to get the negative k over 2 and the positive k over 2 here. That's why I have a plus or minus k over 2. Okay, coming back down here. So what am I doing now? I'm defining a couple new functions: lower circle red line intersection point, very long names, upper circle red line intersection point, as lists, in other words, as points, where the first coordinate is the x coordinate of a pink point, and the second point, element of the list is the second coordinate of a pink point. Notice I'm plugging this thing into the line function, getting the z second coordinate in each case. And this one has a minus sign here and here for the lower circle, which is the bigger circle. And this one has a plus sign here and here for the upper circle, which is the smaller circle. Once again, though, so I got to define those functions. I guess I already did that. Once again, though, I'm interested in when do I have a point of tangency and not two intersection points. When is this thing equal to 0? So I'm solving that equation for r, which you could do with the quadratic formula by hand, and get these two answers. Okay. So what am I after again? So these are going to be radii, r values of the two circles. For any given fixed m and b, for an arbitrary slope and intercept of the red line and ultimately the red plane in 3 dimensions, these are the radii of the circles or the spheres in 3 dimensions that will be the Dandelin spheres that just touch the lines or the planes in 3 dimensions. This one is for the lower circle and sphere, which is the bigger one. This one is for the upper circle and sphere, which is the smaller one. Here again, to be not confused by that, it's important to realize that b is actually negative here. Remember that I said that at the beginning, b is negative here and here. And also m is between 0 and 1, so this quantity, negative 1 plus m squared, is going to be negative as well. That's helpful for understanding this quantity is actually bigger than this one. The lower refers to the lower circle or sphere. The upper refers to the upper circle or sphere. All right, this is a bunch of complicated code. What does this code do? It's going to generate a two-dimensional version of our animation. Can change the slope, can change the intercept, and the key thing is all the green circles and all the dots get updated correctly. Is it possible to understand this code in a couple minutes? Not really. Let me just quickly highlight things here. You could take a picture of it if you like, or a screenshot. I will just quickly summarize what it does. I should first probably say show combines different graphics into one picture. So that's what the show does. This is plotting the upside down V and that's blue, and the red line. This is plotting the two green circles right here. The graphics thing here is plotting all the dots. The magenta or pink dots here, the orange dots in here, and then the two black dots where the red and blue intersect right there. I didn't explain how to find these values here, but that's not too hard actually. And then this is just formatting, and then all that show, which goes from here to here, is inside manipulate that makes the animation, or again M and B vary, and label style large just makes these larger. Okay, so that's the two-dimensional version of what we're after. Now on to the three-dimensional version. What's going to change? Okay, and the key thing to realize here is that, how do I point out this? There we go. The black dots essentially become the ellipse. That again, in the original animation I colored brown and orange. for when y was positive versus y negative. The two pink magenta dots become the foci of the ellipse. Okay? And the orange dots are the yellow circles in the original picture that were at constant values of z. That's what's going to happen. Okay, on to the three-dimensional representation. To make it as nice as possible, the first thing that I'm doing is I'm actually going to make three-dimensional axes with parametric plot 3D. This is not a real big deal, it just makes it a little nicer. So I've essentially stored, well, it's this picture right here, in a variable that I'm calling axes. Okay, the semicolon just suppresses the output. Next, I'm onto a function whose graph is an upside down V, or I probably should say cone. Now we're into the cone case here. I'm calling it cone. It's a function of two variables. And essentially this is the higher dimensional version of the negative absolute value function. Its graph is an upside down cone. And I can enter that and I can see its graph. There it is. Okay, and I've stored this graph in a variable I've called cone, and I can re-access that variable without retyping all this stuff. That's the benefit of setting the graph equal to a variable, which seems funny, but it's a capability of Mathematica. Then I've got a function whose graph is the plane. I'm calling it plane, of slope m and vertical intercept b. And notice its equation, z equals mx plus b, isn't any different than the line. It's because the y doesn't affect things. You might wonder, well, couldn't the y affect things? Well, yeah, for an arbitrary plane like the one we saw, it could depend on y. However, you can always change coordinates. You can rotate your axes in such a way that the x-axis is the dependence of z only depends on x. Okay, there's got a positive slope in the x direction, but a zero slope in the y direction. So we don't get any dependence on the y here. And we can graph this plane and store it in a variable called plane here with a lowercase, okay, to get this graph. Or we can make an animation of it. Let's see, I'm going to manipulate here, and we can change the slope and the intercept. Okay, although you need to switch around these b's here to make it go the right order. That b gets bigger as you move to the right there. That's better. Okay. I actually won't need that animation, but I wanted to just show it to you to illustrate it. Functions of three variables have graphs with contour plot 3D that are level surfaces, and spheres are where a function like this would equal 0. X squared plus y squared plus z plus k quantity squared equals r squared would be the equation of a sphere whose center is on the vertical axis, the z-axis, of radius r. Center down at 0, 0, negative k. Here's a specific sphere where k is 3, so it's centered at 0, negative 3. And the radius is 2. By the way, I can rotate these pictures as well, like that. And I can make it manipulate. But again, getting back to that one comment that I made, alternatively, it's going to be better to actually use graphics 3D as far as three-dimensional rendering goes. This makes the same picture, the same animation, but runs a little faster than contour plot 3D does in Mathematica. I'm going to define a function that I called sphere graphics 3D as a function of k and r that I can use to make such a graph for any value of k and any value of r that I want, and that'll just make the code a little easier to understand and easier to type. All right, take a deep breath. Now it's going to get even tougher, okay? But this is the key if you really want to get all this. All right, I'm about to try to first represent the ellipse that I'm after. Where the plane and the cone intersect is the ellipse. So I want to solve the equation for where the cone and plane are equal to each other. By the way, I didn't mention this before, but when you use the solve command, you need to use double equal signs, and that is essential. I want to solve it for y as two functions of x. And that's going to correspond to the two sides of the ellipse, one where y is positive, one where y is negative, where I colored them slightly differently, one side orange, one side brown. Not that I had to do it that way, but it just seemed best to do it that way. And I can use these equations, these expressions, to define parametric representations of each half of the ellipse. Parametric curves, parametric equations, there are different ways of saying it. Calling them ellipse positive and ellipse negative, corresponding to whether y is positive or y is negative. X is the parameter. That's why in the original animation, X was the top slider, and when I changed X, the black dot moved around. Its X coordinate changed, and its Y and Z coordinates changed as well by these equations. In fact, I used the negative one because that was where in front of the picture, so you could see it better. In both cases, the X coordinate is X. The Y coordinate is given by these two things which come from solving this equation. And the Z coordinate is mx plus b because these points on the ellipse are on that plane that is intersecting the cone to give the ellipse. It's going to be handy to also define a function that represents the distance between the vertex of the cone to the parametric representation. It's just useful for programming. I may not even mention it later. Let's visualize the ellipse in the case where m is 0.5 and b is negative 1.5. These quantities here are just the limits of x for the ellipse. It's the x coordinates of the black dots in the two-dimensional picture. I didn't talk about how to find those. Here is a picture of the ellipse. One half colored orange where y is positive, the other half colored brown where y is negative. Again, you can rotate this more like that. That would be like the original picture. Okay, so we are building up. We're getting close here. Now it gets even more complicated. I want the coordinates of the foci of the ellipse, the pink or magenta dots. Okay, I used lower circle red line intersection point and upper circle red line intersection point before in the two-dimensional situation for the x coordinates of those two pink points as functions of r. Here they are again. Kind of complicated. What I'd really like to do, though, is I'd like to figure out how those coordinates depend on just m and b for both, let me say, spheres now. I'm not talking circles anymore. For the spheres in the three-dimensional picture. So really I need to plug in the r lower and r upper functions in for r into these equations. Into lower circle red line intersection point and upper circle red line intersection point. I should probably call them spheres instead of circles here. This is going to give the x coordinate of the pink or magenta dot tangency between the Dandelin sphere, that's the lower one, and the plane. And this one's going to give the x coordinate of the pink dot, that's the intersection tangency point of the upper, smaller Dandelin sphere in the plane. Kind of complicated. They involve m to the fourth minus 1 as well in the bottom instead of m squared minus 1. Let's see here. I need to take these things and see, actually these are both x and y coordinates, x and z coordinates. I need to take these things and plug them into a list with 3 entries, 3 coordinates, the second of which is 0, because these pink dots are in the plane where y is 0. Their y coordinates are 0, just like in the two-dimensional picture. Here's their x coordinate, and here's their z coordinate for both the lower one and the upper one. So these are going to allow me to graph the pink dots in the three-dimensional picture. Here's a picture of everything in the case where m is 0.5, b is 1.5, and the x, which is going to tell me where the black dot is 0. So this is, we're almost done, okay? This is the a static version of the animation. Now I just need to use manipulate to get the animation. And then the final thing I need to do, which will still take a few minutes to talk about, is why are the two definitions, the conic section and the sum of focal distances definition, equivalent. The main point, I could let x vary. Still m is 0.5 and b is negative 1.5, so x varies here with this animation like that. How did I make that? I put everything from before inside of manipulate, except I changed all the zeros to x's, like there was a 0 here and here and here. I changed those to arbitrary x's because x is the animation parameter for the manipulate. The details of, I think especially this stuff, are hard to understand, and this as well if you're not familiar with parametric representations of circles in this case. This is graphing the yellow circles that you see that are at constant values of z. But the final animation, the code looks like this, letting everything vary. Let you look this over, you could pause it, take a picture or a screenshot. It's quite long. This does give the final animation. Well, okay, I must have done something wrong. It worked before. Okay, we saw it work at the beginning of the video. I'm not going to try to fix it because it could take a while. It worked at the beginning of the video. I think I did something to mess it up. Well, maybe did I? I think I forgot to enter this perhaps. Yeah, that's probably what did it. There we go. And now I could let m and b change as well. Ignore any error kinds of things that come up. Okay. And again, the key conceptual insight in Grant's video is that the sum of the red and yellow distances between the foci and the black dot is constant because this yellow distance is the same as this yellow distance, this red distance is the same as this red distance, and this yellow plus this red stays constant definitely as you go around because the distance between these yellow circles is constant. But how can you do that symbolically? And technically this brings in a whole other subject, the subject of vectors and dot products. Okay? I could do it without vectors and dot products. If you don't know about vectors and dot products, well, then you won't understand what I'm about to say here. But if you do know about them, maybe you will understand this. I'm letting v be a vector that goes from the ellipse to the lower focus corresponding to the bigger sphere tangency, and letting w be a vector that goes from the ellipse to the other focus points. So the lower one is on the left and the upper one is on the right in the picture. And then I'm using the dot product of the vectors with themselves, here and here, as well as square roots and sums to get the sum of distances. Now the key thing that makes the conic section definition and focal distance definitions equivalent is that this sum of distances should not depend on x. It doesn't depend on where you are on the ellipse. However, its formula is so complicated that even Mathematica's full simplify cannot simplify it down to a constant that would only depend on m and b. You still see x's in here. However, that is deceiving because if you plot the graph of this sum of distances as a function of x for different values of m and b, you do get a function whose graph is horizontal, constant, no matter what m and b are. This is a visual graphical proof, quote unquote, of the equivalence of the conic section definition and the sum of focal distances definition. The fact that this graph is horizontal, constant, for any value of x. X is the horizontal axis down here. And for any m and b, different m's and different b's give you different sums of focal distances. But for any fixed m and any fixed b, you get a constant. That is the reason why those are equivalent. Thanks for watching the whole video.